So last time we looked at the pre-solved physical models as an alternate way of defining transmission line sections in microwave office. These allow you to do a slightly more realistic simulations when compared to the ideal models which we had seen earlier. Those are the electrical models. So the electrical models don't care about what the material is, what the substrate is, what the dimensions are. It just gives you the simplest model for a transmission line, which is basically it's propagating the phase along the length of the transmission line. So the only parameters you define are the effective electrical length and the characteristic impedance. The characteristic impedance is important, of course, because that tells you the ratio of voltage to current at any point for one direction of wave propagation. So the physical models are useful to get a more realistic sense of losses and maybe other mismatches you might have. But again, these also have limited accuracy. We saw in some of the cases where we entered some parameters it didn't like. Now, that usually means that one should not make transmission lines with those dimensions. But if for some reason you are making that as a structure, then you cannot trust the results which these pre-solved models might be giving at those solutions, because they might be outside the range of approximations they have used to compute some closed form formula to extract the properties. And we looked at microstrip, strip line, CPW, and coaxial, which was the first one we saw, as different forms of usual transmission lines. Just to summarize, that coaxial is always the transmission line one uses for connecting signals between instruments, and the other three are planar transmission lines, and they are used for propagating signals along a chip or a circuit board to get them to wherever they need to go, maybe at the end to a device, or that microwave structure itself could be the device you are interested in. We finished with a very quick look at the full EM structure simulation platform. So today we will spend a lot more time looking at that in detail. And as I said, I will share the links for both the last one and this one, so that you can look at some of the specifics of using microwave office. And after this, you should be reasonably familiar with all the basic elements of this software. So from circuit schematics to pre-solved models to the EM structure. So these are the three main elements. There are many more. One can actually do things, but we will not be looking into that. There are some other tricks and techniques which I will, whenever we encounter them, I'll explain them. Maybe I'll do some today as well. These are useful for extracting useful information from the simulations we're doing in terms of manipulating the data. So there's some level of programming is also possible. I had shown you some very simple ones like defining equations. You can actually do a little bit more, write a few lines of code and let it compute something. So let me go back to this EM structure here. Now see, right? If you have a problem, probably better to come to the sample. So the EM structure has come under this thing, just like the circuit schematics, we have EM structures. And then inside, I had created a new EM structure last time. That is this one. And that just has a name EM structure, but we can give it some other names. So let's see. And then if you double click that, it opens up this window here. it looks like the same circuit schematic window, but here you cannot drag and drop those circuit elements. So we had drawn this thing, but I'm going to delete this and start again. One of the first things you actually do, which we didn't discuss last time, is to actually define the boundary conditions in some sense for this. So from the looks of the interface, you can see that what you're going to be making are actually two-dimensional structures, right? Now, if you look at all the circuit boards I had shared with you a couple of lectures ago, they are essentially two-dimensional in the sense that the transmission line itself is only propagating in two dimensions. And the thickness of the transmission line is very small compared to the other dimensions. And that doesn't play a direct role in these kind of simulations. It's taken into account in an indirect way. Okay? But you still have these structures existing in a 3D space. So, for example, you know that for the circuit board, the dielectric material matters, right? If I don't know the dielectric constant of that, then there is no need to any of the other properties. So the thickness matters. If there is dielectric at both top and bottom, for example, for a strip line, that matters. So those things are all defined in this enclosure setting. It opens up this window. And the main one which we are concerned with is actually the dielectric layers. The other things I will go through after I explain this. They are basically their definitions for different types of metals you could have and different types of dielectric materials you could have. And those are what show up here as these. So there is some default thing which is drawn here. So let me show you, just tell you what it is, and then we will make the ones we need for, say, making a microcircuit transmission line. So this here basically is giving you the cross section of your circuit board and potentially any enclosure is inside it. So what does it mean here? So if you look at right at the bottom here, so I'm referring to this little strip right at the bottom. This is essentially controlled by this quantity which is shown here, called the bottom boundary. And currently it's set to a perfect conductor. What this is referring to is the thing I talked about, that the substrate has to sit on some, usually some metallic surface, or it could be open. Right? You might have a coating of metal, or you might have no coating, and if you have no other substrate, it's sort of free-handing, then it could be open. So you can set what that boundary condition is. So this bottom boundary and top boundary are telling you basically the enclosure in the vertical dimension, whether it's open, whether it's closed, and whether it's approximately open, which means that there's nothing there, or there's a metallic boundary, and you can then choose that metallic boundary to be a perfect conductor, or in this case, two standard options are showing up, tantalum and scap bottom. I don't know why it's called that. It's an inbuilt standard. These two things are defined in one of these other materials. Okay? So this will matter if you really care about the boundaries, conductivity, and how it may affect your simulations. Mostly, just leaving it as a perfect conductor is fine. It will do a reasonable job. And this is the default configuration, that the bottom has a conductor, but the top is left as approximately open. So that's this one. And that is signify the fact that there is no such strip here. Okay. If I change this also to a perfect conductor, you will see a little strip show at the, it's just a visual aid. Okay. So that then means that there's actually a box you are talking about, which has a top metallic layer. That matters in your case. So for example, doing strip line simulations, you would need metal on both ends. Otherwise, it will not. So let's leave it as approximately open for now. This. And then you see sort of three boxes here. So this red one, which is highlighted, then this one, and then this one. These are the dielectric layers. It is entered here as default. The material is given here. So the top one is air. So it's just saying that, okay, there's an open space here before what you call as the top boundary. And it gives you thickness of that layer. So this here is in microns. Units are written at the top here. These things can, the default units can be changed. Global settings. I'll come to this frost scale in just a second. Then you have some dielectric, they're calling dielectric 1 of 0.2 microns, and then another dielectric of 100 microns. This could correspond to a situation where you have a metallic plate, then you have your RF circuit board, which is made of some circuit board material, and maybe on top of that you have some chip, maybe silicon or sapphire chip. So this is sort of representing that. This is just some standard, so it has no specific meaning here. So you specify this and you give the thickness. The draw scale is just for a visual aid. It's to ensure that very small or very large dimensions in your drawing are not shown to scale that it will be very strict. So for example, you can see that this is 0.2 microns, but it doesn't look like 0.2 microns compared to the 100 microns shown here. Right? Anyway, this doesn't even, I don't think it affects the drawing here. It affects it in a different place, I'll show that. But that's just for being able to see this dimension in some compressed format. So that's not, has no implications on the simulation. Just for visual, I'll show you where it matters. So that is basically how you define your dielectric layers, essentially your circuit board preparation.
So basically, we are defining the thing you showed us that.
Yes, the circuit boards.
Just that, not any kind of cavities.
Well, there is no cavity here. The enclosure of the whole system. So there is, first of all, nothing is defined on the sides. So it assumes that you're not going to be trying to simulate a system where you have side metallic walls, which might be the case in a general scenario where your whole thing is enclosed inside a box. But it's usually a bad idea for your transmission line traces to go very close to the edge so that they start interacting with the side walls. So it assumes that there is no side wall problem here. So this dimension is completely open. Only thing it's specifying is whether there is a metallic boundary at the top or the bottom in terms of the enclosure. It's not a box. So it cannot calculate, for example, electromagnetic modes of a full 3D box. So that's why I said it's sort of quasi 3D. You're mostly defining everything on a plane. The vertical direction is only defined with this particular way. Okay. This has got to do with, again, we don't know the details of the actual solver, but essentially this means that you don't have to solve Maxwell's equations in 3 dimensions. You're solving it in 2 dimensions with some approximations, and these definitions allow you to take into account the effect of the dielectric. So it's a simplification of the system.
So,
yeah.
We want to put some microwave drive-in chip in the middle there.
Sorry?
We want to put the microwave drive-in chip in the
microwave what?
Drive-in. I mean, drive-in. I mean, in the middle there.
I'm not following the word. Can you spell it out?
Drive-in.
What is
we want to supply some microwave in the middle there.
No, right now we are not talking anything about what signals we are providing or anything, right? We are talking about the structure, and we are specifically have been discussing transmission lines. So we will make transmission lines here. So what you are looking at, this represents the cross section of the circuit board on which the transmission line is going to exist. right? So what do you need to make a planar transmission line? You need some ground plane, some dielectric material, and some metallic patterns on the top. Okay. That's what we are defining. Right? So there is no signals and things we have not. We come to that. So just as I said right now, if you just are interested in a simple, say, microstrip transmission line or a CPW transmission line, essentially the kind of things we were looking at in our DX line. Right? So this is sort of what we are trying to define now. What is this structure? So there is one, there's a metallic boundary here, there's a metallic strip here, which is the microstrip line, and then you have your dielectric in the middle. This is what we are trying to define. So let me go back to my enclosure. So we don't need so many layers. We in fact only need one dielectric layer and an air layer. The air layer is also not so important in the sense that if you keep the top part approximately open, but it actually is better to always leave that. So I'm going to remove this middle layer, which you don't need. I'm going to delete it. And now we have something simple. So air, of course, is just air. So we go here in materials. And you have these dielectrics which are defined, and there are some defaults defined at the end, approximately open 46. So that will be the have a dielectric constant of 1. So here there is some definition given for what dielectric 1 is. It's defined by the relative permittivity, which is 6.5, and a loss tangent of 0.005. So that is representing the losses. Again, we are not really concerned about losses, so I'm going to define a new material. I'm going to call it TMM6, which is actually a material we use in our lab. It has a dielectric constant of 6, and I'm not going to set any losses for now. So that shows up here. There are things like you can choose how it displays in the visual thing, but it's not that important. And so I go back here, change this dielectric to 6. And if you remember from last time, I put this number 762 microns. That's actually the height of the dielectric we typically use. This again will entirely depend on what you are actually making out of. And then I have some 500 micron cap, leave it as approximately open at the top and perfect conductor at the bottom. So this has now set up the dielectric layers of our circuit board and the boundary conditions at the top and the bottom. Now, the reason for having this air layer also sort of as a convenience here is that the way the software is defined, like how the layers are defined, is that metallic layers always go between dielectric layers. And that makes sense because we want to put our circuit here, right? And this is now an interface between this dielectric here, which is TMM6, and this dielectric here, which is air. So this is something you have to specify, that where the metal layer is. Is it between dielectric layer 1 and 2? Is it above dielectric layer? Is it below dielectric layer? So that's why having that air layer is useful. If you want to do a strip line, then this air layer will also be replaced with the same dielectric, right? You would think that the circuit board is continuous, so you just have to define one dielectric block, but then I will not be able to put the metal in between. Okay, this is not physics or engineering, this is software. This is how you define the system. So, so you now have these things defined. Hit OK. And I come to the enclosure, and I can now start drawing. Now, for more sophisticated structures, you can actually use any CAD software like AutoCAD or other things to draw your structures, and it can be imported into this and then adapted for this. But for very simple things, like simple sections of transmission line, you can just use their drawing tools. They have some very simple drawing tools here. And for a microstrip, you just need a rectangle, right? So here the x-axis is the horizontal axis and the y is vertical. So one little trick is that while you're drawing it, you can press the space bar and it gives this pop-up window so that you can actually enter the number. So if I remember correctly, we needed something close to 1,000 micron wide for getting something close to 50 ohms. So let me put, so dy has to be big, and the length I will put like some 5,000. One thing I forgot to mention is in the enclosure, in the main tab here, you have this grid spacing. This is sort of the resolution with which you can define the parameters, the dimensions on that particular grid. It's only loosely connected to the resolution of the simulation itself in terms of how it breaks things up. But there is some correlation. So if you don't want your structures to be broken into very smaller elements, because the smaller the elements, the more the number of elements you have for a given structure, and the slower the simulation will be. Okay, so this is something you'll have to do by trial and error for a given structure. But now, if you think about this microstrip, which is 1,000 microns wide, and I have a 10 micron grid spacing, that's already a lot. Right? So if you are too fine, the system actually will recognize that, and it does this process is called meshing. You'll see the mesh in just a second. It breaks up the system into these polygons, and then those are where the Maxwell's equation solves. So you don't have resolution within the polygon, it's just the boundary condition. Things, electric fields and magnetic fields will change from one polygon to another polygon. And there will be a boundary condition applied to the simulation. So for now, we will leave it at 10 micron by 10 micron. But you basically can see that grid if you zoom in. So it's this grid spacing you're seeing, these dots, they are spaced 10 micron apart, which means if I try to drag and move this, it will move in these 10 micron units. I cannot do it as a finer step. So that's what that is for. Now, this metal which is at ground, we have to define what that metal is. So we right click it, put shape properties. And then here in material, it says thick metal, which is again some predefined thing. We will just use perfect conductors for now. And it also asks for the EM layer. Okay, so this is where the connection between the enclosure structure we define and where this metal is going is done. And you have to look at the graphic here to understand this. So first thing is that it has defined this as a VR. And that's because and remember, VRs are the ones which connect two different layers through a metallic structure. Right? So we will come to that later. The reason it is chosen that and not giving any other option is because the EM layer is chosen as one. Whereas the actual EM layer we need is this one, which is EM layer 2. Now, this might not be so obvious when you first use it. So I don't know how it counts. Basically, the topmost layer is the top boundary is called the layer 1, or it's the dielectric layers. That's right. So since the air dielectric layer is the dielectric layer 1, EM layer means on top of that dielectric layer. So since the location of the metal we want to put is above this TMM6, which is dielectric layer 2, we have to choose EM layer 2 here. And then we don't have to choose VR, we just have to say conductor. Then it shows you that whatever metal you're drawing is going to show up at this location. You can have more complicated structures with multiple dielectrics and metals in different locations as well. So that this allows you to do that. So even though on this in this diagram, everything will show on the same plane, but the actual assignment could be at different planes. Yeah.
So that there we find it as 750 to 42 units.
Microns.
And here it's 1,000.
That's the 762 microns is the thickness of the dielectric.
Yeah, but then, okay, it's a thickness.
It's this. It's
You're
this
talking about the
thickness.
X-sides.
I'm talking about now the microstrip we are drawing on top of the.
So further lower, we assume the X-y extent is infinite.
So it automatically, there's no boundary this way. The system automatically recognizes based on the structure you have drawn where you sort of stop the simulation. So that's basically it for defining the structure. Now you can sort of get a 3D view by going to this particular thing called View EM 3D layout. This sort of gives you a sense for what you have drawn. So you can see there are these two dielectric slabs and the metal is between them. But in this case, the top slab is there. And then I guess the top thing is labeled red because of the I've selected. And it's this location where the draw scale, which we have chosen here, matters, like how it shows up here. So right now, both the thicknesses are similar, so they don't need different scaling. But just to show you, if I make this 0.1, then it will show the air layer as much thinner. Okay, this is purely for a visual thing so that it looks okay on your screen. Otherwise, if you had a situation where there were two thicknesses which are very different, then you will not be able to see it very clearly. So now you have the full thing defined. So we can now set up the actual simulation. And before we do that, we have to add the ports. So this basically tells you it needs to solve, because at the end of the day, the goal is to compute the scattering parameters, like transmission, reflection. So you need to specify the reference where you're doing the excitation from. So this is sort of related to your question. And for a microstrip, it's always at the edges, right? And which edge? The left and the right edge, because the transmission line is along this way. I can put the ports here, but then it would be a different transmission line. It will be a 10,000 micron wide transmission line, a width and a length of 1,000 microns. So you click. So this is something sort of a bit strange thing. So you click on the metal you want to put the port on. Go to draw, and you say add edge port. There are other types of ports. We will come to that later. And then you go to that edge, and then it gives you this kind of a highlighted thing, and you put it. But you need a second port, so it's the same metal. You can go there, add edge port. So the numbering it automatically takes care of. You have to make sure that you don't duplicate the numbering, because you can actually change them by double clicking it and putting some number. If you do it sequentially, it will number the things. There are some details over here which you will look later. There's also this symbol A which is showing up here. This has to do with this setting here, which says type auto, none, connect to lower. Okay. This is again something complicated and subtle, and I will discuss this in a later lesson. But for most cases, an auto setting would work. This has to do with the ground for that port. Right? Remember, what we have connected is the signal port, the signal terminal, and there is a ground terminal there. So the boundary condition of how the excitation is defined, there are some subtleties there, and it's how the solver actually handles it. So you need to be careful about this, but for most simple structures like this, you don't have to worry about it. You can leave it in this proper settings. I'll have another discussion. This is more about the details of the software, so I don't want to spend too much time.
Which cross section is it? I mean, where are the metals that you put in the design? The bottom metal and the micro,
This is the microstrip.
which is the bottom?
You are not seeing, so in this view, you don't see any bottom because you're only looking at the 2D surface where you're drawing the structures. That was here in this 3D layout.
Yes.
Okay. And what do these things mean? That is here in this enclosure. So there is a metal at the bottom, then there is a dielectric. The metal you saw, the rectangle we drew, is here in between these two. Basically, it means it's on top of this dielectric which is shaded. And then you have air, and then nothing. Is this clear? What you draw in your EM structure here is just the planar part of the circuit. That's all there is to it, right? If this was a CPW line, there will be two more metal on the top and the bottom here. Those are the ground planes. If this was a strip line, then the dielectric definition would have been different, but this transmission line here in this view will look exactly the same. It's just a piece of metal. So essentially, the way to think about it is that you're mostly drawing just what is on your main signal plane. The other dimensions are defined separately in those enclosure settings. So now the ports are defined. The last thing to do is to set the frequency of simulation. So that's done in the same way. You go to the project and you find your frequency list. Now there is one other detail here that you can actually specify the frequency. I think I discussed this in an earlier lecture before when I introduced MicroWave, is that it's possible to define a different set of frequencies for the particular circuit or the simulation you're doing. So in this case, I came to this menu not from here options, project options, but instead I right-clicked the EM structure here and went to options, and then it has given me this frequency. Now I don't know why the project default setting is not there, but if you just click this, then it will take the global settings. But you can specify a different set of frequencies for this EM structure. Now, it might seem like an unnecessary feature, but the reason for this is that EM structure simulations, finite element simulations, are much slower than the circuit simulations. Okay. So you might, in the interest of time, not want to solve it with a lot of detail and frequency, but you want to use the results of this EM structure in a circuit. So this is something we have not seen so far, but anything you create, whether it's a circuit which has many components or an EM structure which has many ports, they can all be used as a sub-element in a different circuit. So you can solve for like different components and then combine them as a circuit by just connecting the ports in a circuit schematic. I'll show you how that looks like after we finish the simulation. But it's in this kind of situation where you have two different sets of things running, because simulating simple inductors and capacitors in a circuit is instantaneous for all practical purposes. EM simulation can take seconds to minutes to hours. So what Microwave Office does by default is that, let's say your frequency rate of interest is between 4 and 5 gigahertz. Okay. For the EM structure, you might just solve it at 10 points or 11 points at 100 megahertz spacing. But then you want to use that in a different circuit which has maybe some inductors and capacitors. Maybe you're making a resonator which has a much sharper resonance, and you want to be able to look at that in a much finer grid. So what Microwave Office will do, as long as the frequency range is within the total range. So what I mean is, in this case example, 4 to 5 gigahertz. You can go to a small frequency range like 4.5 to 4.55 and have 100 points there. It will basically interpolate the data it has and it will recompute it just from the existing data. This works only if your EM structure's frequency response is assumed to be a smoothly varying thing. Now, for things like transmission lines, it's usually like that. But if you simulate an EM structure which is supposed to have a very sharp resonance with very few points, then you're not going to be able to see it. So this requires some thinking about when you can do this or not. But it's very useful to actually run the simulation in a short period of time. So I'm going to not use the project defaults. Instead, I'm going to give a much coarser frequency spacing here because this is just a transmission line. I don't particularly care. And so now for the EM structure, it will only solve at those 10 points. There is another catch here, and this is something you have to be careful about. Because I didn't create the EM structure again today from the beginning. We had looked at it last time at the end. Let me just go back. It's got to do with this solver. Remember when I created the EM structure? In fact, let me just do one to show you. When I say new EM structure, it pops up this window with a list of simulators. And then we chose this first one, XEM. Now within XEM, there is an option which shows up in this window under XEM. There are some things related to the solver's configuration. Again, for most of these things, we will not go into any details. But there is this one particular one called the advanced frequency sweep, and it's currently enabled. This tries to speed things up even further by actually looking at the trend of how the solutions are changing as a function of frequency. Okay. So it's like if you already knew that you expect the response to be something smooth, which means that the S parameters are changing in a smooth fashion as you go from one frequency to another, versus the solver itself trying to see is it smooth, and in which case it doesn't need to even solve all the points you have specified, and it will just create an interpolated curve by itself. Okay, now this can terribly go wrong if your structure has some very sharp features and it's not able to catch it. So this has to be used judiciously depending on what you're trying to do. So if you disable the enable frequency sweep, it will solve for every frequency point you have specified. But if you don't do that, or if it is enabled, then you will see that it will solve for a few points and then it will basically keep the full curve. So, all right, so that is done. Let me go to this graph and create two measurements, S21, which is a transmission, and I'm going to look at the magnitude, and I'll add one more, S11, which is the reflection. Just to show you, okay. Put all the four possible ones here. That's fine. So this measures reflection at this end, reflection at that end, transmission from here to there, and That's it. Now I can hit this analyze button. Okay, this is strange. Saying it's having some license issues. Strange because it's running. The license system. This company has configured this software incorrectly. I mean, you never tried EM structure simulation on this computer, right? हेलो लेकिन तुम्हारा उधर अभी किशोर है क्या वहाँ पे? एक सेकंड बात कर। अच्छा हाँ किशोर ये जो W105 के डोर के पास जो कंप्यूटर है उसमें देखो माइक्रोवेव ऑफिस भी खुला हुआ है and it has a say login. Do you see that error message? Yeah, I don't know what's going on. It's basically not simulating the yield structure. Just or it's okay. New yield structure. It's right. Oh, it's in layer 2. Perfect. It's in the right place. Course. Come on. Seems to be working now. Okay. All right. Just want to show you something. So there's this option called mesh. This is something which the system will automatically do, but I can do it separately so that you can see what it has done. So this has now gone to that 3D EM layout view, and it's now showing you how it has divided the box, the entire structure into different boxes. So you can see that it's definitely not a 10 micron grid, because this entire thing is 1000 microns wide, and maybe there are about 10 boxes here. It does sometimes it does some weird things like right here in the middle, it has chosen some finer grid points. It's not a joint, it's the same line. This is some peculiarity of the software, but usually what you will see is whenever you have boundaries, you will do something like this. So maybe it's actually because it's close to the boundary here. And it also has done something strange, which I will discuss later when I talk about the ground reference point. That here, the box boundary is sort of shown somewhere in this location. Like what I mean is that the box boundary is shown here. Shown here, but this, you see this part here, this is actually how it is creating that ground reference. So between that point and that point, but it's not at the same location. This has got to do with how it uses reference planes and things like that. So it's again a subtle thing about details about simulation, not too important right now. I'll probably have 1 or 2 sessions later on where I discuss some of these subtleties in detail. It's not really related to the understanding of the microwave structures, but more about how we use these kind of softwares so that you don't get wrong results. So this is something, just a warning, especially with EM structure simulations, what you get could be completely misleading if the simulator is misbehaving or you have set it up in such a way that the simulator doesn't do things right. So this is the mesh part. So let's go back to the it's actually not even started.
So whenever you open the software, it shows this error message about something wrong with the license.
So right now,
In the other PC.
in the other PC, I see. Okay, I think I'll have to check the.
It's not exactly error message, it's a warning.
Also, the license gives access to various different features. Like for some reason, it's not configured correctly. I mean, we use EM structure simulations all the time, but this is something else. I mean, I remember now that on this computer, sometimes we were having this problem that once we start the simulation, it takes like minutes before it actually starts the thing. Just wait for a minute. The shift discussing something else while it does it. That's the background. So you have just a refresh it. All right. Does this look okay?
Compare with the translation between
Okay, apart from that. What were we expecting to see? What did we make?
the expected translation, some reflection, even in the calculus.
Yeah, but
And the sentence of that frequency, we're expecting some translation, some reflection, depending on the calculus.
yes, but did I design the microstrip with something in mind?
Yeah, you were keeping all the dimensions so that it has 50.
Let's go back to our calculator. Constant 6 with 5, 7, 16. Thickness we didn't really specify in the EM simulation because it was assumed as a perfect conductor. Length was 5,000. 53 ohms is what the calculator predicts. So that is close enough to 50 ohms. So if you just have a nice 50 ohm transmission line with nice 50 ohm ports on either side, what do you expect in the transmission? Just one, right? Everything is so, which is basically what you are seeing, but as Pania pointed out, some point it is giving 1 point. So this is actually one of the, it's interesting, on the first pitfalls of finite element simulations. Even though you think that the software should do it, because this is an unphysical situation, but this is a numerical calculation, right? So if things don't balance out exactly, you can get results like this. So this is one of the things you have to be careful about. Of course, if you're just designing a transmission line, this doesn't really matter that the result is slightly off. You're seeing that it's mostly unit transmission. Look, I mean, there's some funky shape here, but look at the scale on the y-axis, right? This is irrelevant on the scale of what we are usually interested in. So I can put this on a more 0 to 1 scale. 1.1. Looks decent, right? Let's look at the other 4. It's now reflection. 1. Transmission in the other direction. Reflection of 4. So it hasn't plotted them yet, and I'm going to have to simulate. It's not going to actually re-simulate the whole thing, because once you simulate the EM structure with the ports defined, it internally knows everything about that system, which is basically the estimator. So plotting it again will not actually ask it to recompute the whole thing, so it will come instantaneously. So let's see. So if we just look at now the reflection as well. So reflection here is basically close to 0. Okay. And you expect that since most of it is transmitted, the reflection is going to be low. And you also see that S21 and S12 are, it's going to disable the reflection so that oh, I guess I will not be able to see it. Yep. Let's move back. So they are lying exactly on top of each other. Now, this again by definition is a property of any linear reciprocal network. We will look at these properties of S networks in one of the upcoming classes when we look at this whole network analysis in detail. But for a passive circuit like this, there is no difference between port 1 and port 2. So S21 and S12 will always be the same. But the reflections need not be. So in this case, because the system is completely symmetrical about the axis between the two ports, there is no difference, right? It doesn't matter. I look at it this way, that way. So that's why the reflection, two reflections are also identical. Okay. Now here again, because of small numerical errors in the calculation, you could see some differences. And if they are very small, you can sort of ignore them. But they are usually signs that something is not going correctly. So the one thing we can't really say from the simulation right now is what the length of the transmission line has really done here, right? Here in this, because it's close to 50 ohms, there are no reflections, so we're not seeing any periodic patterns. So in order to look at that, you have to look at the phase. So I'm going to create another graph and plot the phase of the transmitted signal. Angle. And you see this phase continuously increasing from some low value close to 0, some negative value around -120 degrees. This is because for the same physical length, the higher the frequency, the smaller the wavelength. So if you think in terms of how long the transmission line is in terms of number of wavelengths, that essentially tells you the electrical length, right? Or the phase you will get as the wave will propagate. So 180 degrees would have meant it's lambda by 2, but at this frequency. So what it's telling you is that our transmission line's length is about 125 degrees at 10 gigahertz. Now, let's see what this guy computed. And you can see it's exactly the same. Right? So this is how you know what the length of your line is in DM structures kind of simulation. You can compare that, see if that part has worked out. Maybe just to see if things looks like an ideal simulation for that. So make this much smaller. And let it run in the background. Yeah, there seems to be a combination of problems about the AWR running on that computer, plus also things not refreshing through any disk. Like it usually gives you what it's doing here. For some reason, that's not updating. But maybe that has something to do with the AnyDesk remote desktop connection. So just to summarize the essential things you have to keep in mind about these finite element simulations is that if you're not careful about setting it up, and there are other subtleties which we'll discuss later about the ground references, but for most standard things, it's not a problem. And you have to keep in mind these kind of numerical errors which can creep up. You cannot trust them blindly. Okay? You need to have some idea of the physical system you are actually trying to simulate. You know it from knowing about the structures, so that you can then take the results and interpret them correctly. Now, usually problems can happen because your mesh is not finely defined. Now, for a very simple structure like a straight transmission line, this is of very little consequence. But if you have structures involving transmission lines of different dimensions which are interfacing, then if you don't tell the simulator that it needs to look very carefully in those transition regions, which means the meshing has to be more precise. It usually does that by itself. It recognizes that things are changing a lot faster. It needs to make, and in fact, we can see that maybe in an example by just looking at the mesh, how it changes near boundaries. And sometimes you might be impatient that, okay, the simulation is taking too long, so I will just reduce the mesh size. We haven't seen how to do that, but there are some default settings which tell the software that you can use high density meshing or medium density meshing or auto meshing. So you can force it to make the structures coarser, and then the risk is that your results might not be very accurate. But in many cases, you're only looking at trends, and for that it's okay. But if you are trying to get the characteristic impedance to 3 places of decimals, which anyway has no meaning, then you cannot really trust the simulations. So now this was a deliberately reduced transmission line, and now you are starting to see the effect of the reflections. You're getting this periodic. If it was much longer, because we did not even have 180 degrees there, this thing would have repeated itself after that. Right? But if I make the transmission line longer, the simulation will take even longer. But you again see that effect that at very low frequencies, these kind of mismatches have very little effect. Because effectively the length of the transmission line is too short to have any transmission line type of effects here. And they start kicking in at higher frequencies that the transmission is now no longer close to unity. The reflection is coming up as well. So this seems to be working. Let's now try one other about the meshing part. So what I'm going to do is I'm going to use this to show here. There is this equal slicer. Cut. Now I'm going to make this one larger. One other feature about these EM structures layout is that if 2 pieces of metallic structures are, like here, there are 2 separate things, I just have to bring them right next to each other like this. This means that they are in contact. This means they are not in contact. This is also okay, but now the effective length is going to be on the edge here. It will not complain because not like one going on top of each other. So you just have to make sure that they are in contact, and this can be just a trick thing that if you are zoomed out, you might not be able to see that whether they're actually in touch or not. So the reason for drawing this is to look at how the meshing changes. So I'm going to, so if you're under EM structure, you see this thing here. This is actually the mesh object. So I'm just going to delete that. Then I'm going to ask it to remesh. So now you see it has done some interesting things. So on the smaller dimension side, it is mostly uniform rectangular grids. But out here, see how it has changed into more polygons, like triangles here. But again, these are algorithms which are written by the software manufacturers on how they decide to do this. To me, this looks strange. Can you tell me why?
So, at boundary condition, they are trying to be more accurate, but the sudden change.
That is the good part. That is how you would expect, because you don't, something interesting and exciting could happen in those abrupt changes. So you want to have more spatial resolution in your simulation. But there is something obviously strange here for me, which doesn't seem to make intuitive sense. Again, of course, this is their software. So
This side.
exactly. Like, what's so special about this size and not that size? Right? The boundaries coming from both directions. You would have imagined this to extend up to here and then become regular squares again. So I don't know why that is. So sometimes these things are a bit random. You will see that it will do it. And again, if I zoom out, it has repeated this again over here. See, it comes back to the regular grid, but now it has repeated it over here. Even again. So, these are related to details of how they have written their software. Some of these things, I think you can control, you can force it to do a specific way. But I guess we noticed this last time also. We can also look carefully on the edges. It does some spinal boundaries. Because again, the edge of a metal is where there's a discontinuity, right? There's a different air or dielectric on the other side. So it makes sense that it tries to solve it in a more final way. And it understands the dimensions that here it's shorter and there it's longer. So it only looks at the edges. So sometimes staring at the mesh might suggest, if your results are weird, you can look at the mesh and say, okay, maybe this is why, let me try something differently. So the mesh density can actually be controlled here. Shape properties. Here there's the mesh. And here there is something called use document specific. Those are generic conditions. So if I do this, and in the mesh features under destination, it gives you these different options. So this is the smaller thickness ones. If I go to high here and redo the mesh, somehow. So it must have some other overriding thing that it realizes the structure is too simple to need very fine mesh, so it doesn't do it because I think it's trying to optimize the solver time. But for smaller structures, definitely use this. So that's it. So let me quickly show you how to set up two other types of AM structures, and maybe you can try this running it. I'll not run it here because it takes time. Let me get rid of this piece here. It's trivial to turn this to a strip line simulation. All you have to do is take this dielectric and make that also TMM6. Make this thickness the same as the bottom one. Okay. Because remember, the metal was defined in between these two, right? Right. Go back to the 3D. I think the metal definition probably got stuck. Not I have a weird suspicion about it. So maybe doesn't like same name, but that's strange. Let's create another one called PM6A, same properties.
So should we make upward open instead of open conductor?
Oh, well, that's not the reason for the error, but you're right that for the strip line, I have to make the upper one also perpendicular. Otherwise, not work. No, this was some solver related error which was coming, which seems to be solved now. Strange. I will double check this and send an email. So what I have done is I've created, even though these two directrix are the same, I've just given them two different names. This was just an intuition that maybe that was the problem, but I don't see why it should be like this. Maybe it's something here. So this is the strip line. Now, if you look at the 3D thing, right? It's the mesh. So you see how the ground reference looks different now. So it is automatically realized that there are now two grounds. So the port's ground reference is done from both ends. So that's why this yellow and the pink things are different. So that's how you make a strip line. Now we go back to single-ended substrate and show you how to CPW. So this is again something specific to AWR's microwave office, how it does CPW. So CPW basically means you need another ground plane on either side. But you have to define the ports in a very specific way. Because remember, there's still only one port on either side, but you need to somehow specify that this metal is related to the ground. So you choose some gap and widths. I'm just putting them at approximate locations right now. But what you have to do in order for this to understand that that is ground is you take these ports which are defined on the same side of port 1 and you define them as -1. Similarly, on this side, define them as -2. This ensures that there are only effectively two ports, and also it tells that this is the ground reference for this thing. So I've never looked at this reference meshing for this. It's done that. That's what it does. It's even a whole bunch of has something to do with. So what has happened? This is version 16. Like over the years, they have changed some of the default products to automatically remove the auto one. That makes this also fun. Let me just try one last thing, otherwise I'll just check this and tell you next time. So I recently have simulated this fine. So it's got to do the ground reference. I'll check this in more detail. So if you now just to show you here the measurements, if I go to add a measurement for EM structure, it will only give me 2 ports. So because there are only 2 ports, I cannot change this. So as long as your gaps and the widths are chosen for a 50 ohm transmission line or whatever you're designing, this would work. Okay, so you can stop here, and I will send you your first homework tomorrow, and then we will meet again on Friday. So this Friday I might have to move the class, but I will confirm that by tomorrow because I have some visitors coming overlapping with the class. Once I get the exact time details, I will make sure we do. Okay, all right.